Very good morning, all. So, I hope you have enjoyed the confluence, etc. And now we can start with the class again, back to the technical discussions. By now, I'm sure that graph implementations and graph related programming you have done and you are practicing it in a good way. So, by now, graph and those programming clarities are over. And today, we go to another important paradigm of the algorithm. So we are going to see effectively algorithmic strategies one by one now. And in the initial class, first or second class, I defined effectively 4 strategies. And we have said that we are going to cover each of them. Well, directly or indirectly, we might have covered some of these, but now we will see one by one in more detail. So I listed initially that there are 4 categories of algorithmic programming, and one is called as a divide and conquer. Second one is known as a dynamic programming. Then third one is known as a greedy approaches or greedy approach. Let me just correct this. Greedy approach. And of course, then similarly, we have the fourth one, which we call as effectively nothing but a backtrack. Of course, with the direct name, you have used divide and conquer in quicksort, merge sort, and many graph algorithms. Indirectly or directly, you might have used somewhere, but now we are going to see how they will be used. The important point of all these is their applicability is with certain special conditions. So applicability is based on specific characteristics, and accordingly we have to find out some specific preconditions or characteristics which meet, and if they meet, only then I can say that this is going to be a problem related to be solved with these categories. So like for divide and conquer, we have seen that quicksort and merge sort could be used in that sense. But of course, when I said like I have not done similar process with insertion sort or selection sort, although they can be recursively done, but primarily we use the divide and conquer for this. Similarly, directly or indirectly, greedy also somewhere we have used. We probably will find that backtracking also somewhere we have used, but not very sure whether we are aware of this or not. So effectively, today we are going to start with dynamic programming, and which is going to be one of the fantastic and most interesting paradigm of the programming. And special so because many of you have not thought the programming in that direction. I'll not introduce what is this. I'll go through an example, and then through there only we will discuss and find out the characteristics and then see what dynamic programming is all about. So I have another interesting problem, which we call as a road cutting problem. So we will see what is road cutting problem and then discuss their implementation and other issues. So I say, I have a road of, let's say, wood or metal, let's say of size n. So although the problem, we are talking of a real life problem, but I use n so that effectively the input size comes into picture and applicability to algorithms or computer science and engineering is being discussed. That yes, that's what we are supposed to do, but that's a real life problem. Everybody wants to have the best profit, best earnings. So this also says get the maximum revenue. Maximum revenue by selling it, by selling this road in one or more pieces. So in one or more pieces mean effectively that road can be sold either a single piece or it can be cut into multiple pieces. And if multiple pieces, each piece will be individually sold. For example, if I say road is of size, if the road is of size 1, road is of size 2, road is of 3 size, 4 size, 5, 6, 7, 8, 9, 10, and so and so. And the corresponding profit, I say normally profit, say let's say P word I am using for this. Let's say the profit or earning I'll get is 1. If I sell a piece of size 2, I'll get profit 5. Let's say this I'll get profit 9, 10, 8, 9, 10, say 17, 17, 20, let's say 24, 30. Similarly for 11, let's say 36, and so on. So there are so many sizes available. And now I can easily see that corresponding to this, I will obviously require this data to be stored as an input, etc. So you can see effectively the profit array is available to me as input, and based on n, all profits are available. Say, let's assume n equal to 5. Now I want to say what can be the maximum revenue I can generate by selling it. From 5, obviously I can see now this can be sold as cutting it into 5 pieces. So each of piece 1 size, or it can also be had, I can have a piece of 2, another piece of 3, or I can have piece of 1 and 4, or I can have piece of 1, another 2, another 2. I can also have piece of 1, 1 and 3. I can have 1, 1, 1 and 2, and many more like that. Obviously, I can see a lot of permutations are possible, and the profit will be different. For example, in this case, the profit could be 1 plus 1 plus 1 because of this. In this case, a 2 plus 3 size will mean 5 plus 8, 13. In this case, 1 plus 4 will mean effectively 9 plus 1, that is 1 plus 9 profit. In this case, the profit will be 1 plus 5 plus 5, and many more like that. So probably I could say 5 plus 8 could be better, or maybe I can find something more also, maybe better than that. But obviously, if I have this, I can see there are going to be many permutations and combinations, and I have to find the revenue or total profit. So total profit effectively is by selling all pieces of that size. That is equivalent to, I say, revenue for each of these permutations, each of possible permutations, and the best is to be taken and maximum is decided. So when we say such kind of a problems, I want either a solution out of multiple solutions, one with the maximum or one with the minimum in other cases. Such problems are called as optimizational problems. So these problems in general are given name as optimization problems, where effectively what we mean is find an optimal solution. Many solutions exist. Find an optimal solution out of many possible solutions. So there are many solutions possible, and many possible or feasible solutions will exist. Possible, or I can say feasible also. Feasible could be a better word. But optimal will mean one which has maximum profit. In this case, for example, or I'll say maximum revenue. Profit word I'm using for a single piece. So I'm saying, say, maximum revenue. Similarly, sometimes it could be, let's say, minimum cost for some other problem. So in general, I say, I want to have the either maximum or minimum as per the problem. And such solutions are called the optimal solutions. So the optimal solution means one which has the best options or best offer in terms of maximization or minimization. So the optimal solution we have to find out. And optimal actually means either maximize or minimize as per requirement. So in these problems, now we have to find out a solution. Obviously, I can see that now lots of possibilities, many permutations and combinations. How to generate these many permutations and combinations? Probably recursion could be the intuition, or recursion will be used most likely. But if we are doing that, then we have to find how effective we are doing that. So now from here, let's say road cutting. So I'm saying road cutting for a particular size. First thing is, if I have to do permutations and combinations, how many permutations and combinations are possible? Accordingly, probably I have to think of recursion, and accordingly the implementation. Based on this, we have to do. So I have to roughly see. So mathematically, can I tell how much? That way it will help me to solve further. So then I have to systematically solve that if I am given a size of n, on one step, can I divide it into sub-problems? So if I'm given size n, can I divide it into recursion? Means if I think that recursion has to come, effectively recursion means that divide into one or more sub-problems of smaller size, one or more sub-problems of smaller size, which can be obviously recursively solvable of smaller size. Smaller size will mean, of course, less than n, and each sub-problem is recursively solvable. Then only recursion will work. So if I have to do that work, I can say I have to systematically design the solution recursively. So in this case, for example, I say at position equal to 1, should there be a cut made or not? That can be one way to go to sub-problem. If I say no cut, the size will remain effectively one piece only of size n. If I make a cut, for example, let's assume n I am taking as, let's say 4, n equal to 4, say. So I say piece remains of 4 size versus one piece becomes of 1 size, other piece will remain of 3 size. Now I say position equal to 2, should there be made a cut or not? Obviously, at position 2, if no cut is made, then this will still remain size 4 piece. Cut at second position will break this piece into size 2 and 2. Similarly, this side no cut versus a cut. So I say no cut and I say yes cut. So no cut will mean first piece remains 1. At position 2, no cut made. So this piece remains as it is. But here, if second position also cut is made, first piece is as it is with nothing. Second piece has been cut. So that will make one piece to be of 1 size and a right side piece to be of 2 size. Similarly, for position equal to 3 also, I can have a cut or no cut. I can further get 2 cases for each of this. And obviously that is over because no further cut at position equal to 4, nothing because size is 4. So maximum cut can be at position 1 or 2 or at 4. So I can say effectively if n was 4, I have 8 permutations possible, 8 solutions possible, or I'll say 8 permutations possible. Effectively meaning that 2 raised to n minus 1 solutions can exist if I grow like this, and recursively it can be solved and I can generate all solutions, find out the maximum or best solution, find the optimal out of these. But that means I have to generate all these 8 solutions. Well, good enough, can do if n is, let's say, 10,000. This is going to be very big and this grows exponentially because it's a power of something. So this mathematically, I know it leads to an exponential growth of the size. So if I have something like a 2 raised to n minus 1 pn permutations and combinations, the algorithm running for n equal to big size for big n will be effectively very time consuming, can take days or years on a computer, on a normal computer. On a supercomputer, we might do, but on this is going to be really taking so much time. Of course, we can't afford that. So we say such algorithms are called to be having time complexity as exponential. On the other hand, till now what we have done is time complexity of a polynomial was better, obviously, desirable, because even if it is polynomial in nature will mean some algo has n square, n cube, even n power, let's say 6. All these are polynomial, but for bigger n, still affordable, still workable, still solvable, still not exponentially growing. Hence, they can be still solved in a reasonable time. So obviously, we will prefer to have polynomial solution than exponential. Of course, for certain problems, it won't be possible, but there will be certain situations then where exponential solutions can be converted. So if possible, try to convert exponential solution into a polynomial algo. And if you can do that, it is definitely a good contribution in the algorithmic design. So we are going to try for certain solutions or certain problems like that. But of course, all problems will never be solvable. So certain characteristics will be desirable. Like, so coming back to the road cutting, I say, if I have to now, knowing that characteristic, so effectively knowing that road cutting problem, I can see that now I have to solve it in a way that I can divide it and find the solutions. So first aim will be aim to find some optimal solution, or aim to, I'll say, characterize optimal solution. Characterization means try to just find that recursively, even if it is to be solved, how can we do this? What to do? I say I have a road of size n. Let's assume that we have some special powers and somehow we are able to identify that break at some position k. Say I say cut at k is desirable. Guaranteedly it is correct and this gives optimal solution. So if this I know, then I can say, okay, if I make a cut at position k, I will mean one piece will remain of size k and other will become n minus k. For example, let's say I have size as 5. So I could say that one piece, let's say, of size 2 is desirable, other of size 3. This much I know. 3 can be further solved, 2 can be further solved in some way, but somehow I know this cut is must. If I know this, I say, now I can solve the problem probably easy. So if k is known, I can say that now the problem will be easy to solve. So my aim will be to find such k. For example, if I say I have got n as a 5, k could be 1 also, k could be 2 also, k could be 3 also, k could be 4 also. So all possibilities are there. So I should try every one. This is what I mean, finding the optimal solution, designing the solution one by one. So effectively, now I may say that k has to be identified and through that I will be solving. But let's say I know one side is 2, other side is 3. Then what can be the maximum revenue for this? This can further have possibility 1, 1 or 0, 2, etc., etc. From here also I want maximum revenue. So from here the revenue will mean maybe 1, 1, 1, maybe 1 and 2, maybe 2 and 1, maybe 0 and 3, etc., etc. So still I can say recursively probably I can solve all this. Recursively that can be further solved. But if I know this cut, then I can say, if I was saying that maximum revenue corresponding to cut 5, so I say Rn represents maximum revenue possible with size n. So if I assume that maximum revenue is represented for size n as Rn, my R5 will be nothing but revenue generated with size 2 plus size 3. Of course, I said if cut at 2 was must. But the advantage of this is this I can recursively find. This I can recursively find. Hence, this can be one characterization. Effectively, this I consider my first step towards recursive solution. But obviously, how do I say cut at 2? Obviously, no guarantee. So if there is no guarantee, I'll prefer to find out the position also. So now I say my maximum revenue with the size is nothing but I should try with cut at every position, try with every position, find out the cost for or revenue from out of that, and that can be one. So RN can be the best or maximum out of either if I get profit with the same size, no cut at all, or cut made at size at position 1. Position 1 will mean one piece will be of size 1, other will be of size 1. This is again recursive, same Rn using same word again. So this similarly, it could be R2 cut made as second position and then Rn minus 2 and so, ultimately going the cut being at Rn minus 1 position and then R1. So if I find all possible cuts are considered, or indirectly I say which K I use considered, so I will be able to guaranteedly get answer. Reasonably simple, this logic works, but effectively this is nothing but a recursive definition possible. And this is effectively programmable now easily. And this normally is my step 2. Of course, formally we will define later, but I'm just giving you that this is another important step. But primarily step 1, 2 are similar and we are able to find something. Then I say, now what next? The recursive definition over. And now I can program, but I say, if I see, for example, R8, so this will mean I have to find maximum out of what? Either piece of 8 itself sold, maximum revenue through this permutation, maximum revenue through this permutation, maximum revenue through R3 plus R5, or R4 plus R4, or R5 plus R3, or R6 plus R2, or R7 plus R1. But if you see carefully, in this space, so this is good enough, can work generally, but for this problem, I can easily see that this solution versus this solution are same. So probably we have many duplicate solutions and we can reduce that. So we can reduce some, that is one thing, because they are duplicate. But the most important aspect now, think if R7, how it will be solved. R7 solution will ultimately also require max out of profit of 7 plus R1 plus R6, R2 plus R5, R3 plus R4, etc., etc. But indirectly what it means, this will also calculate R5. Here also R5 calculated. Here also R5 calculated. This R5 will also calculate R5. So I can see that R5 and many others will be calculated many times. Many others will be computed or will be computed a lot of times recursively. If I implement recursively, they will be computed many times and every time answer will be same. But recursion implementation effectively meaning that this will be calculated a lot of times. It's a time wastage. I can save some time. And that becomes the crux of DP problems. So the basic characteristics is most important point to be identified, that this is a dividable problem, So it is a kind of a divide and conquer also, because the sub-problems are recursive. Sub-problems we have already defined. Sub-problem based solution we have already done. Optimal solutions. So divide is also there, but sub-problems are overlapping in nature. That is the most important. Why I am saying sub-problems are overlapping? Like when R8 is being used, it requires, let's say, R5 also. It will also use R7, R6, and so and so. When R7 will be calculated, that will also use R5. R6 will be calculated, that will also recursively compute R5. And not only that, here itself in R8 itself, R1 plus R5 needed, R5 plus R1 needed. So we have a lot of duplicacy, and within their sub-problems, there is overlap. So R5 also doing this, R6 also doing, similarly for R2, R3. Think, if let's say I'm talking of R100, maybe R5 thousands of times or thousands times it will be calculated. 1,000 times or even more times. 1,000 times or maybe million times or lakhs of times. And because R100 will use, R99 will use, R98 will use, and R99 will see recursively again need R98 multiple times. So R100 will also use, R99 will use, R98. Then R98 will also go. This R98 will further contribute towards R97, but R97 will be done by R99 also, R100 also. So every time exponential growth happening. This can be improved, and that is the logic. So I'll say, what is the solution? Why to calculate every time? You can always say, store R5 for first time, store R5 somewhere and reuse it, and don't calculate again and again. If I can do that, obviously time can be solved or time can be reduced. So that is the crux of this. So I say divide and conquer problem versus a DP problem similar. Both have sub problems which are optimal. But in DP, they are overlapping. In divide and conquer, quick sort. I said one partition as a sub problem, optimal. Second partition, sub problem, but this solution was independent of other problem of part 2 or partition 2 or sublist 2. I'll say I had earlier a sublist. So in case of quick sort, sublist 2 solution has nothing to do with the sublist 1. Sublist 1 will further get solved easily. Further division will happen. This will also divide it into further smaller lists. This will divide it into further smaller lists, bigger or smaller, but independent. In DP, they are not independent. Sub-problems have overlap. And overlapping can be helpful to solve problems. So effectively, what we will do, such problems will have initially exponential time complexity, and we will be able to convert it using DP to polynomial algorithms. And that is the crux of whole DP. How to do? We will systematically understand. So our aim is to reduce recursive calls and try to have storage also. So of course, extra space is needed. Of course, that is a trade-off always. Extra space will be definitely needed. And we are ready to afford because the time is more important. So I say, if I have, let's say, size of 4, I want to find out R4. I say, for revenue out of this, I will say profit out of 4 or R1 plus R3, R2 plus R2, or R3 plus R1. Obviously, overlapping visible and partially they are duplicate also, like here. So one way could be that, yes, I should not go to this at all. But I say this can be further improved, that instead of this, I can probably in this problem, I can solve it with less recursions also, not only reducing the duplicacy, but also in this problem, less recursion can be done. For example, I say, don't cut the left piece at all. Still, answer will be similar. Don't cut left piece at all. And this duplicacy, which I was doing unnecessarily, that can be avoided. No duplicacy or less duplicacy will happen through this. Like this is a duplicacy above. This is a duplicacy. Even if overlapping, but still this is straight away duplicacy. Might not be another problem, but in this problem. What does that mean? I will say, I claim that R4 can be still solved by making it as either P4, and then I say P1 plus R3, P2 plus R2, and P3 plus R1. Remember, here I have made P, it is a non-recursive. It's direct profit array. I have already this input. You might say that situation like this gets P1 and R1 are similar, so no problem. This is straight identical. I say equivalently, I am writing this. But how to prove equivalence in this problem? How do I say R2 plus R2 can be considered as a P2 plus R2? Why? How? How this should be acceptable? Maybe not correct. R2 means with size 2 also maximum revenue to be computed with size 2. But that will be possible means there are only two possibilities, either the whole piece of 2 size or this divided into 1, 1. For R2, there are only two possibilities, effectively meaning R2 can be calculated either using P1 plus P1 or it can be calculated as directly P2. This R2 is equivalent, so I'm not bothering. This is okay. So I'm trying to see whether when I said R2 plus R2 permutation above, and I said that I need not go into R2 plus R2, I can just use it as a P2 plus R2. I say this has two possibilities. One possibility is this R2 will as it is continue. I don't bother about this. So this will mean P1 plus P1 and R2 as it is. Or because of this, let it be P2 and R2 as it is. Now I say, when I wrote a P2 plus R2, this is okay. When this is here, where covered this? Where is this being covered in a new solution, in equivalent solution? So I prove that yes, this is also covered. P1 plus P2 plus R2 solution will be covered indirectly in P1 plus R3. Why? When I say P1 plus R3, R3 will be solvable either as P1 plus R2 or P2 plus R1. The other two possibilities, it's a recursive. Recursively, it will be solved in the same way. So if it is solved like this, this total will mean equivalently, this solution means either P1 plus P1 plus R2 or P1, this one P1 and second also. So I say P1 plus P2 plus R1. Now I said this case is covered in this. So by writing the solution as maximum out of, so if I said Rn equal to maximum out of a Pn versus P1 plus Rn minus 1, P2 plus Rn minus 2, and Pn minus 1 plus R1 is a better solution because half of the recursive calls are not needed now for this problem. And if I can do this, it is directly programmable and less recursion needed. Still exponential, but probably better. Still exponential, still overlapping. Of course, why overlapping? I can easily see like Rn minus 1 will internally call and calculate Rn minus 2 also, Rn minus 3 also, and so and so. So Rn minus 2 will be needed for this calculation also. Rn minus 2 needed here also. Rn minus 3 needed for this also. Rn minus 3 needed here also. Rn minus 2 will still require R minus 3 also. So multiple times overlap. So still it is not the best solution, but better solution. Can I do programming? Can I do write recursive code for this? Recursively? Simple. Above solution I can write. I'm giving you time, just write down. And in the meantime, I will rewrite that solution, that my recursive solution for size n is nothing but maximum out of. So I say it is this what I want to program, profit n and P of 1 plus R n minus 1, P of 2 plus R of n minus 2, and so and so. P of n minus 1 and plus R1. Solve this programming. Well, in the video recording, I'm not waiting, but I'll just wait for pause for a few seconds so that you can pause your video and try writing code yourself. Then I'll write the code. So I expect within 5 minutes, you will be able to write more or less good code of this. Might not be 100% correct, but maybe 70-80%, and that is good enough. Later you can refine. But I say I have to return some value. So I need, let's say, int cut road as a recursive function. Of course, profit array I need and n I need. So this I need, and ultimately, of course, I want to return maximum revenue. So I say I'll write some statement where I will be doing the maximum revenue return. So last line I will say return some variable which will be max revenue for this size. So that will be recursively, ultimately, equivalently saying Rn being returned. I have to calculate. How to do that? Simple. I have to find maximum out of n values. So logic is simple, but recursion means always conditional. Unconditional cannot be. So stopping criteria. Of course, I can say if n is equal to 0, means guaranteedly profit is 0. I can simply say, here, effectively return 0. That's it. Else what to do? Of course, if n is bigger, I have to use this formula. So I'll say, let's assume my some variable max revenue initialized with, let's say, Pn. So Pn is known to me. And then out of all this, I have to find the maximum. So I can effectively write, I'll just say, I have to repeat now how many times? For I equal to 1 to n minus 1 times. N minus 1 repetitions do. And what I have to do? I have to effectively say whether this value with I is greater than previous max revenue or not. So if I'll say, if max, I'll just leave one line, later I'm going to use this. So I say, if max revenue is greater or less than currently whom? Pi plus Rn minus I. Rn minus I means a recursive call. That means cut road with P being passed and n minus I being passed. If so, effectively, I am going to update my max revenue. No bracket needed. Effectively, max revenue will be equal to the same value. Now, if you see carefully, this value will be computed twice. Recursion twice, unnecessary. Twice recursion will be called. Why? The same value being recursively again called. Why should I unnecessarily have this? So can I improve this? Of course, yes. I can have some variable taken say recurse val. So I'll just, that's why I left one space. I'll say recurse val equal to this call being generated. So cut rows and p and n minus I. The advantage being, once I do this, this call I can replace by this variable, and that can save my one recursion. So I will say pi plus recursive val, and if it is less than this, so I'll say if it is less than this, no semicolon, of course, then I will say it is equal to pi plus recursive val. But that saves one call. And if so, ultimately, if something else to be done, I can think of anything more to be done, but more or less, I have found the maximum. And finally, the return. So it's very simple. Recursive call being generated for each n minus I, and that way I am able to do straight up simple code. I am sure you can write without a difficulty. Why I am again going further, let me just save it. And this code or this slide I will leave. So I'm just saving it at some place. And this slide I'm copying paste at the last. And that I will use again after some time. Okay, fine. So now let's resume here. Having said that, this becomes a recursive implementation without a difficulty. Simple. But you can easily see this is a permutation combination problem. And obviously, I am going to have a lot of recursion. So effectively exponential time. And the solution we have already thought. Why calculating every time r some n minus I? Why should I calculate Rn minus I multiple times? Why? So I can definitely solve this problem and improve. And that's how DP will help me. So solutions. Ultimately, solution is simple. Store Rn minus I. Means I will take an array. So I will take array R, and R will be 0 to n. So I will store whenever R0 is ready, whenever R1 is ready, I will store R2 is ready, and Rn is ready. Ultimately, each of these I will store so that recalculation is not done. How to store? How to get these values? So effectively, what I need is a DP solution, which is ultimately called as a bottom-up solution. Why bottom-up? We will understand. But there is another solution, which we call as a memoized solution. Memoized solution effectively means memorize after calculating first time. It means first time you will calculate, but after that you will store it and memorize. But it is a top-down solution. It is not called as a DP solution. It is not a DP solution. DP has to be non-recursive. So effectively, it will still remain recursive, but we will improve something. What improvement we will do? We say, for example, you are calculating R5. R5 will internally go to calculate recursively. It will generate call for all of them. It will generate call for R1, R4, R3, R2, R1. I said it is going to generate call for P1 plus R4. So R4 will be recursive. P2 plus R3. So recursive, similarly R2, R1. When R4 will be called, so first of all, R4 call will come. This will further require R3, R2, R1. R3 call will come then slowly. That will further require R2, R1. R2 call will further come again. That will again require R1. R1 will come. That can be calculated and stored. Then this will be non-recursive, and I will store it in R array 1. So in R2 or anywhere else, like from here also R1 needed, from here also, every time whenever this call will come, I will check if R1 is already calculated, then don't calculate again. Already calculated, use it. Otherwise, use it. Otherwise, only you will calculate. So for effectively here, it will be calculated first time and stored, but other calls will subsequently be able to use. But that looks difficult probably, but programming wise, that will be so simple. What will be simple? We can see easily that first time I will check. So I'll say what I will do. I will say, I'll just, sorry, let me go and go resume with certain slides. So I'll say this and I'll copy some of these slides. And later I'm appending so that I can just continue. Yeah. Okay. So from here I resume. So I say I have to calculate. So I say I will have one function. Maybe I'll say memoized. I'll say I'll write one function for memoized cut road to start, where initialization, etc. I will do parameters. I will decide. Here I will say I am going to take R array and R0 to n minus 1. Each of them will be given value minus in infinity, means not calculated at present, because minus infinity means nothing done yet. But whenever I am able to calculate the value will be either 0 or more will mean calculate. 0 or more means it is calculated. So I'll say I wanted this. So I'll say Rn, R0 to n minus 0 to n is initially this. And then I will call memoized cut road recursive. Now this cut road recursive, of course, I will require P to be passed. So this is an array. I will have n to be passed and also R to be passed, which is an array. So this recursive I have to make, which will be calculating or reusing. Now, what is going to be memo cut road recursive? So I'll say, here I have that slide available, which I will just use now with a different pen. So I'll say, nothing special to be done. Here, I'll just change my color. I say, I will make this function to be memoized cut road recursive in nature. And of course, here I am going to pass. So I'm not R also. So this is additional I'm going to use, and this is the function name. Firstly, what I will say, I'll just remove this. Firstly, I will say if Rn is already calculated, means if Rn is greater than equal to 0, effectively I will return. That's it. Effectively, that is the logic. If it is already calculated, return. Otherwise, before returning, I will store Rn equal to max revenue. So next time it is calculated. So now you can easily see that this whole logic will calculate Rn, and Rn will be stored into this variable and returned. And anytime a next call will come, that will reuse this. So rest adjustment I have to do. For example, in case of n equal to 0, I'm saying return 0. So before that, I will say, let's say R0 equal to 0, so that R0 gets modified and now call over, because this was recalculated. For other cases, initially maximum revenue is based on the profit initialized. That will be 0 or more profit. Then all permutations tried, that will recalculate max revenue. This call will be generated as a recursive call. So I will say this call will be still memoized. I'll say, or I'll just remove this, and I'll say instead of this call, effectively this call will be memoized and cut roads recursive in nature. This function which I have made, and I will pass it p n minus I and r. And based on that, this will be again using the same function. Done. So effectively, this is what I mean with this. So effectively, I mean I have my int memoized cut road recursive, which is being passed the corresponding p as an array, n being passed, r being passed. Syntax I am not writing, and exact code I am not writing. You can write. And of course, first thing will be I will check if Rn is greater than equal to 0. I can simply return the same Rn without calling the recursion. If n equal to 0 means for n equal to 0, this is being calculated first time. Earlier R0 is infinity. So I must make R0 to be, R0 was minus infinity. So I'll make R0 equal to 0. And I will return this R0 or return 0, whatever you say. And else I will calculate. So now calculate Rn effectively. Or I'll say calculate maximum revenue because Rn is not calculated. Calculate maximum revenue as earlier done recursively, more or less same code. And then finally, I will say Rn equal to max revenue. And then, of course, I'm returning. So whether you say return Rn or you say return max revenue, one and the same thing. But this line will be effectively memoization. So having said that, I will say now I will stop here and I'll ask you to read one sub-problem graph concept given in Corman that is explained in the book Corman 3rd edition itself in the chapter. In chapter 15 it is given. So just read, that is another characteristic of DP problems. And then you must remember Fibonacci series now. So Fibonacci series, effectively you said Fn equal to Fn minus 1 plus Fn minus 2. Effectively you see Fn minus 1 will also use Fn minus 2 plus Fn minus 3. So these sub-problems are overlapping. And when you had this sub-problems overlapping, this was again a DP problem. So if you recursively solve, it will be very slow, but you have also generated effectively F0, stored it, F1, stored it, F2, and slowly you went to generate from 0 to F1 or using 0 and 1, 2, using 1 and 2, F3, using 2 and 3, F4, and you were able to generate it from this way. So this was effectively nothing but a bottom-up solution. So this was effectively DP solution. And you used an extra array in Fibonacci series. If you go without recursion and use one extra array, you were able to solve. So you have used DP in that concept without actually knowing how to systematically reach there. So we have now defined that. I'll just quickly summarize that your problems which have optimization requirement. So optimization problems we are talking of, they have optimal sub-problems as a solution. Optimal sub-problem based solutions exist. But if the solutions have overlapping sub-problems, then we call them to be effectively nothing but these are going to be a DP based problem, and they are different than divide and conquer problems because of this overlapping. And this strategy is different. Then these are a DP category, and effectively we can use extra storage and bottom-up based solutions can be created solutions generated, bottom-based calculations done, and solution generated. This will be guaranteedly leading to a polynomial solution. Earlier, this, if solved through recursion, this was going to be recursion without memorization meant exponential solution, exponential growth, or exponential time complexity. So the exponential problems of a DP nature can be converted to time complexity of polynomial, and that is the advantage of via DP. Having said that, I'll wind up here. I'll quickly ask you to implement at least recursive and memoized one, and DP solution we will talk in the next class. Also try to read a sub-problem graph and Fibonacci series concept, that is unsolved question 5 in the chapter immediately after these discussions. So just go through that, revise that, implement at least the recursive and memoized, and next class we will understand DP solution and then solve 2 standard problems, MCM and LCS, one by one. Bye-bye, all the best, have a good day, enjoy. Let me wind up my class now. We'll stop recording. Very good morning once again, and let's continue with the discussions on the road cutting problem. And we have already seen the discussions related to making it a DP problem, how it is a DP problem, and how we have discussed, primarily talking of having the sub problems to be overlapping, that is a must. So it's a divide and conquer, but overlapping sub problems. So this is effectively the main characteristics, and effectively divide and conquer was also there. So divide into sub problems, recursive, that was also being done, but along with overlapping. So that's it's a DP. And then we talked of having the recursive implementation, and then we also talked of a memoized implementation. So both, and then today we are going to continue quickly with the DP. Just have a look. This is what we talked of, a recursive implementation. And then we talked of this as a memoized implementation. So just stopping here and showing you quickly the code. If you have done, good enough. If you have not done still, we can discuss the coding of this. So here I go with the first recursive implementation. So once reading the profits, etc., primarily here is what we read. So this is cut road, profit, and n being passed. Revenue will be generating. So if n equal to 0, return. Otherwise, I'm starting with revenue max to be given profit of n, and then making the loop to be effectively going for all that implementation of 1 to n minus 1. This is a recursive call being made for n minus 1 value, n minus I. And this recursive value I'm using so that I need not recalculate updation and then final return. Of course, this loop can be made up to less than equal to n also. And in that case, revenue max of profit will directly come from here. And then in that case, recursive value will be automatically 0 if n is equal to 0, etc. So I can alternatively do that way also. Doesn't make much of a difference. It is more or less same. Coming to equivalent, the memoized version. So I say I will be initializing all values to a negative infinity. And then I'm going to call the recursive memoized version of this in this way. So this is road or memoized recursive version. R will be passed here. Of course, if R is already generated, I am returning. If n is equal to 0, now R is also updated and return is also done. Otherwise, the logic is more or less the same. So that is the same. Additional change being that this here I am again updating and then return. So whether return revenue max or return RN, one and the same thing. Effectively, to be more precise, I will prefer write here return RN so that it is clear that RN has been now calculated and I can return this. So that way I can always have this value implemented. So this becomes the implementation for the memoized version, and otherwise this was for the recursive version. So this is for the recursive one. I can see here I have the recursive call. In memoized, Rn being checked, If not available, then only the recursive call will come and initialization, etc. Now, so having done this, let me stop and resume where we have already discussed, and then from here, now I go to the further discussions about making the further improvements. So memoized was one solution we have said, but as we said, memoized solution is a bottom and is still a top-down solution. When we say bottom up, effectively a DP solution means, or dynamic programming based solution means, that we have to do it as a bottom up fashion. Bottom up fashion effectively means that I should be able to generate the corresponding value starting from the lower values up to upper. So effectively bottom up means, say n equal to 0, R0 is effectively non-recursive. I know already. So R0 is known to me. Effectively from R0, or without that, I can generate R1. Then using these or two, I can generate R2, because R2 will require effectively calculation of R1 and, or I'll say R0, or maybe R1 definitely. Then similarly, once these three are ready, R3 can be calculated without any recursion, because R3 will ultimately require these three. Why? If you just recall, R3 is nothing but, we said maximum out of profit by n, that is profit by 3, and then we said P1 or profit or P, I'll use word so that we don't get confused. So I'll say we will use here profit 3, or then I will use P1 plus R2, or I will use P2 plus R1. So effectively, if you see here, it will require either R2 or R1, both are ready. So R3 can be directly calculated. In fact, I will make it even more simpler, that I will say R3 is nothing but equal to maximum out of, I will put everything as P1 plus R2, P2 plus R1, and then I say P3 plus R0. R0 is already known to me as 0 definitely. So R0 is here 0. I say R0 will be equal to 0. You can easily see. And once I have R0 as a 0, I will say now I can also put, instead of saying P3 separately, I can put it here this. This just gives me advantage that I can be taken as 1 to n. Earlier I was taking I as 1 to n minus 1. So that is it, but otherwise more or less the same thing. So one end is the same thing, but I can see now R3 can be generated. So effectively each Rj can be generated non-recursively, can be computed non-recursively using the stored values, using effectively R0 to Rj minus 1. And those values are being calculated every time. So primarily, this I will claim is called as a step 3 of my DP solutions. So DP steps are effectively 4 steps. So this will be step 3. In detail, we will talk in the coming discussions. But just say, yes, this is a major step. Once done, then finally, I have to effectively calculate Rn effectively. That is it. So Rn to be computed, and where are the cuts being stored, or if the cut positions, if I have to store, so cut positions can also be stored and they can be printed. So for cut position storage, you can use array C 0 to n, telling that if where is the first cut, say C1 will be the first cut where you are going to use. So whenever R1 is calculated, for R1 corresponding cut details, you can store in C1. Similarly, corresponding to R2, wherever the cut is, you can store. And if you want only the maximum value, that value is already being returned. Rn is the last max value already returned. So that is already available. We have stored. So effectively, if I have to do the coding, coding will be very simple. I can say, yes, I have int cut road, but it is a DP solution. Of course, I have the array P being passed. So if I have the array P being passed, I have the N being passed. And if I need anything, I can pass, but probably now I'm not. So R you can also pass out. R you can make as an array being passed so that R will be stored. And of course, R is initially either uninitialized or not. Now doesn't matter because I am going to use bottom-up solution. So obviously, first of all, I have to effectively say that R0 is to be computed without any recursion. So I can say R0 equal to 0. That is non-recursive by default. Now I say I have to calculate effectively Rn. So Rn means, first of all, I have to calculate R1, then using R1, R2, then using both of these R3, then using all three R4 like. So effectively, I mean, I want to calculate Rj and later j will reach to this. So I'll say for j equal to 1 to n2, and here what I want to do is compute Rj. Now compute Rj, effectively, I have already made the logic. Compute Rj is nothing but this is equivalent to saying max out of R1 plus Rj, or not R1, I'll say P1 as per the formula, P1 plus Rj minus 1, P2 plus Rj minus 2, P3 plus Rj minus 3, and so Pj plus R0. So profit Pn or Pj I am taking with R0, and R0 is already there. Now this logic is nothing difficult. I can easily say so I can take max revenue as we have already said. So effectively I will say max revenue equal to minus infinity. And then for I is equal to 1 to n do. And then using R's, effectively you can update if max revenue less than something. But here, of course, I will use R words. So effectively, I can say Pi plus Rj minus I. And then accordingly, you can update anything to be done. And then finally, once you are out, you will say Rj is ready and Rj equal to max revenue. And then this process to continue. And then finally, you will be ready with the Rn that is to be returned. Now, here, if the result or answer, here you can put answer related updations also. For example, just I said answer related C array will be there. So those updations, etc., you can maintain here. And then accordingly, C will also be ready. So in that case, this C can also be made as a parameter. So that also can be made as a parameter where results or cut positions can be stored, can also be made as a parameter. So if you want just the total profit or total revenue, that is already available. If you want individual cuts info also, that you can use. So this effectively becomes the overall DP solution. So quickly summarizing DP works or DP steps, primarily, first of all, what we did was we had characterized the problem and characterized the corresponding solution. Then from here, effectively, recursively, I defined the solution, recursive definition I found, and then I tried to generate or compute the corresponding bottom-up steps for individual value. Bottom-up way I calculated, I'll just say bottom-up. Calculated bottom-up Rj. And then finally, I generated, or I'll say the final solution. Of course, if required, that means Rn definitely, and plus if the cut positions also required, they also can be accordingly prepared. Yeah, prepared using the above step. So those we are able to do this. So primarily, you can see main two steps are there. Here I have recursively found the solution, then I converted it into the bottom solution. So here the recursive solution or permutation solutions, and then from here I try to convert it into a bottom. So with this, I'll stop, and maybe next class we are going to discuss more relevant and standard problems, because this clarity will come to you and help you in better understanding.